Winter's night, isn't it? Long weekend and all. Any new members here? Yeah, a few good faces. Welcome, guys. Anyway, yeah. So another introduction to astronomy session. Just getting this used to this. So, okay. So what are we going to talk about tonight? Well, as you know, you didn't exactly see this morning when you got up, did you? The strange appearing over the sky. But the bottom line is, the sun is critical to us. It's critical to life. It provides us with heat, warmth, drives our weather patterns and so on. And I read the other day an astronomy book written by a lady, and she says, clearly the sun is a woman. It works tirelessly, provides heat, light, non-stop, reliably, for a family of 8 planets, and it hasn't had a holiday in 4.6 billion years. I thought that was quite funny. So it was good. So yeah, it's the sun is critical to us. We rely on it 100%. Wouldn't be here if it wasn't there. So to me, that begs the question: what do we know about the sun, and what more do we need to know about the sun? That's why tonight's talk is titled "The Sun, Our Nearest Neighbour." What's going on? Our nearest star, rather. What's going on and why? So there's 3. I always like to start and finish with 3 sticky messages for you to take home. First of all, over 99% of the mass of the solar system is all in the sun. Really, the solar system is all about the sun. We're just crumbs. Someone once, I remember a question being asked of a solar astronomer, and they said, is it possible, how likely is it to get planets around a star? And the answer was, have you ever tried baking a cake and haven't spilt any crumbs on the bench? It's just almost impossible. So it's all about the star. And as I mentioned, it's vital to life on Earth. The sun generates energy through nuclear fusion of hydrogen to helium. And that automatically makes sense. That's of huge importance to us because that's such a clean, efficient way to deliver power, far more efficient than the current nuclear fission that we use. So if we want to get clean power and learn to harness that, a good start would be to learn how the sun does it. And the third sticky message to take home, that solar events like your solar flares, your solar prominences, your coronal mass, ejections, things we're going to talk about tonight, all of those are due to distortion of magnetism. 3 sticky messages which I'll repeat at the end of the talk, but those are key points to take home. So we're going to do it with these sort of main 5 chapters, if you will. Split it into parts. Part 1 is going to be the sun in context, in the context of other stars in the galaxy. That'll be chapters 1 and 2, some facts and figures, and then how the sun, how it was born, and how it's going to lead its life and evolve and so on. So we'll go over those briefly. And then we're going to focus on chapters 3 and 4. What's going on inside the sun? How is it working? And then all about that magnetic activity that's going on and how it affects the solar cycles. And then we'll finish up with a summary and our 3 sticky messages again. And I've got 2 videos implanted in the talk, which are quite good to see on the big screen, and it just brings the topic alive as opposed to a boring topic on the sun. I've purposely got some, because the sun's amazing. It's a busy place up there. It looks pretty quiet when it looks at the horizon, but it's a busy place. Videos are the best way to... So yeah, let's have a look at the, so chapter 1, the introduction, some facts and figures. The sun in context with other stars in the galaxy. So first of all, the sun is a star. Often people ask, what is the sun? It's a star. So what is a star? A star essentially is a luminous spherical ball of plasma. And you might say, well, what's plasma? It's the 4th natural state of things, of material. The 3 that we're most familiar with on Earth because of our temperatures and pressure systems and so on is solids, where you've got neutrons and electrons bound together quite nicely. Solids, where they're all stacked up nice and neatly. Then you've got liquids, where things, the atoms, complete atoms with electrons and nucleus, quietly, a bit more fluid, it moves around. And then you've got gas, where these atoms are bouncing around all over the place. Well, if you get one of those gases and heat it up to extreme temperatures, the electrons are going to be disassociated from the nucleus. But it's behaving like a hot gas. So essentially you've got electrons and atomic nuclei just all running amok. And that's what plasma is, except it's really hot for it to have got into that state. And stars are held together by their own gravity, hence they're spherical. So what is our sun made of? 73% hydrogen. And you probably recall from high school days that hydrogen, the atomic nuclei of hydrogen, is just a proton. So it immediately tells you that most of the sun is just electrons and protons just running amok, zip-zapping all over the place in chaos. 25% of it is helium, and then 2% of it is a mixture of other elements. Oxygen, carbon, neon, nitrogen, and iron. There's a big long list of them there. But they make up only 2% of the composition of the sun. So how hot is the sun? Well, first of all, if you go right deep into the core of the sun, it's 15 million degrees there in the centre of the sun. And that's how it enables to fuse hydrogen to helium, which we'll talk over briefly. And the surface of the sun is roughly about 5,800 degrees Kelvin, which is still pretty hot. And what do you notice there? Everything, this is like a common you see in everyday life. The middle is always hot and it gets cooler as you go out. Hang on to that thought because that's quite relevant with the sun. Okay, so the sun is at the centre of our solar system. Its distance from Earth is what they know as one astronomical unit, which is 150 million kilometres, or as light travels, 8 minutes and 19 seconds of light speed. So a photon of light from the sun to the Earth takes 8 minutes, 19 seconds to traverse that 150 million kilometres. I actually put that in yellow there, so you'll see a lot of your handouts. I missed out the one, so I wrote it in over the top. Now, how much larger is the sun in relation to the planets? So I've just told you the sun makes up over 99%, so here's some interesting figures for you. The sun accounts for 99.86% of the mass of the solar system. So it works out to about 2 times 10 to the 30 kilograms. And that's for relative sizes there. The radius of the sun, actually with mass, and as the gentleman pointed out, there's a typo in the handout there. I've got 130, left out 3 zeros. So it's 330,000 times the mass of the Earth. So you'll see that on page 1 if you just to add a few zeros on the end of that. And size-wise, the radius of the sun is 109 times that of Earth. So here's your big sun on size scale. There's Jupiter, there's Saturn, there's Uranus, Neptune, and there's Earth way down here. Yep, tiny compared with the sun. So you really, until it's spelt out like that, you underestimate just the sheer size of the sun in relation to the planets. So where in the Milky Way is the sun? Well, this is a picture of a spiral galaxy. It's actually Andromeda, our nearest reasonably large spiral galaxy. Why haven't I got a picture of the Milky Way up here? Because, of course, we haven't travelled outside the Milky Way to take a picture of it. So, but this, for all intensive purposes, does the trick quite nicely, a picture of Andromeda. So if this was the Milky Way is about 100,000 light years across in diameter. A light year being the distance that light travels in a year, and travelling at 300,000 kilometres per second, that works out to 1 light year is 10 million kilometres. And the Milky Way is 100,000 of those light years across. We sit out here, that's the centre, sort of going out to the suburbs. We're 26,000 light years away from the centre of the Milky Way, so a little over halfway out into the suburbs. That's where we sit in the Milky Way galaxy. This is another diagram looking directly down on where we are, and here's the sun here. So here's the nucleus of the Milky Way. This is a nice little diagram, and here's your sun about halfway out along. Now, the other thing is you might ask yourself, well, how fast, if the sun and everything's going around the centre of the galaxy, how fast is it going, and how long does it take to do a full orbit? Well, you don't realise the sun, or our whole solar system, is travelling pretty quickly, roughly about 230 kilometres per second. How fast we're whipping around the galaxy. And the other side of that, however, it's a long way around here, such that it's roughly, it works out, it's quite easy to remember, it's a galactic year is roughly about 230 million years. So when we were in this spot last time in the galaxy, the dinosaurs were roaming around.
Yeah, the one on the left, Chris, has got a million that shouldn't be here.
What's that? 230 million kilometres per second? Oh, sorry, yes, pardon me, yep. Yeah.
Which arm do we see as the Milky Way?
Oh, okay, so wintertime, like now, we're looking in the southern hemisphere, we are looking, well, it's our winter rather, and yet now we are looking back towards this way here, towards through here. So you've got the Perseus arm, now which is Sagittarius arm, and here it comes around here. Yep, here it is. So wintertime, we're looking towards the bulge. You know Sagittarius? This is facing towards Sagittarius here. Summertime, we're looking up this way. So what sort of, people say, well, what is the star? How do you classify the star? What is it? And most people say, look, it's a class G25. And we'll say, oh, okay, G25, what does all that mean? Stars are generally classified by what they call their spectral class, and it's a whole talk in itself. Just briefly, the spectral class in the letters O, B, A, F, G, K, and M, for historical reasons, they're out of the normal alphabetical order. That's a whole different talk. But the bottom line is that relates to its surface temperature and its colour. And G class stars, and then there's O through to 9, O being the hotter, and of course you go up to 9, so each one's split into 10 subgroups. And the G classes are sort of a green to white colour from space, and the temperature of a G2 star is 5,800 degrees or thereabouts. Now, how about the 5 bit at the end? What does that mean? I've just put here stars get bigger with increasing spectral class surface temperature, and we're way down here. So those are your big OBs, and we're way down here. So we're not a big star by any means. And this is what they call the Hertzsprung-Russell diagram. And it's where they, once again, a whole talk on its own, but just brief introduction. So if you plot the surface temperature of stars along here with how bright or luminous they are up here on the y-axis, you can quite conveniently, stars will find themselves in little patterns. And there's one particular strip that goes right up through it here called the main sequence. And this is where 90% of stars sit, and stars spend 90% of their life on this main sequence, where they're in a very, very stable state, burning hydrogen to helium at their core. And that's, by definition, makes them on the main sequence. And the sun is on the main sequence. And it is, and that's what the 5 stands for. I think I've got a slide of that. No, I haven't. So I've got this actually this is a bit of humour. Yeah, so the 5, all these little groups here are represented by different Roman numerals, and the 5 means that we're sitting on the main sequence. So when you see that we're a spectral class G25, it means, okay, our star looks it's a greenish yellow tinge, mainly white. It's got a surface temperature of about 5,800 degrees, and it's sitting on the main sequence burning hydrogen into helium in its very natural state. Yeah, I just found this on the internet. I just tossed it up there. Everything's got to come down for maintenance, doesn't it? Just a bit of humour. Okay, so chapter 2, let's talk about how the sun came about, how old is the sun, and what will eventually happen to our sun. So that all stars start their life in the mix of one of these things called a giant molecular cloud. These are huge clouds of gas and dust in interstellar space. They're hundreds and thousands of light years across, some of them. And the bottom line is something will trigger whether the whole cloud or part of the giant molecular cloud will start collapsing in on itself. And there'll be small little dents, little knots lying in there, and they will continue to collapse down and to form stars. And this is sort of the process underway here. Big stars always develop first, those big OB stars. So there's a lot of gas and dust still lying around, but the process has started where some of the big stars have already been born and starting to blaze away. Our sun may just be getting underway, possibly at a stage like that. Then you end up getting, once all the gas and dust has been used up or blown away, you get a nice open star cluster like this. This is M67. There's some suggestion our star possibly could have come from this cluster. But the bottom line is you get a nice open star cluster like that. And eventually those stars do run their way. As I mentioned, as the star forms through collapse and spinning round and round and round, planets can't help but this lovely big protoplanetary disk here where planets will form, which is us. This is a cool picture. This is from the Atacama Large Multi-Millimeter Array. A high-resolution image is your new star being formed here. Look at all the disks going around. You see new planets are starting to form, picking up all the dust and gas. So the sun is 4.6 billion years old. How do they know that? Can anyone tell me how they know the sun is 4.6 billion years old?
Uranium lead.
Yeah, and the bottom line is radioactive dating of meteorites. This is a meteorite. And not all, but a lot of meteorites are just pure, pristine, primitive representations of the initial rocks that formed out of that protoplanetary disk. Because they haven't been on a planet, they haven't undergone geological processes. So if you do radioactive dating of these pure, pristine meteorites, you can get an indication. So the indication is the sun's about 4.6 billion years old. So, which means it's about halfway through its lifetime. It's expected to spend, a G-star spends about 10 billion years on that main sequence. So when our star runs out of hydrogen in the middle, it's going to become a red giant. Here it is here, leaving another 4.5 billion years. It'll leave the main sequence to become a red giant. That's once again another whole talk on stellar evolution, but the bottom line is a red giant starts to swell and swell and swell. If that's the sun now, that's what it will do. It'll come right out to Earth's orbit. And of course the habitable zone is the zone, because of the heat from the relevant, the parent star, is the zone around it whereby liquid water can exist on its surface. And yay, of course, we are in that habitable zone. But look what's going to happen. The habitable zone is going to get pushed out to Jupiter and Saturn as things get rather hot on Earth. And we will look like that perhaps in 5 billion years' time. Andrew sent me some interesting stuff. We were just discussing, what are we going to do about it? I don't know if we'll still be around, but obviously we've got to do something about it before then. There's talk that we might be able to push Earth out into a further orbit, into the habitable zone again, possibly. All sorts of solutions to that. Or we might go in, if we're still around and we haven't blown ourselves up, of course we may have by then moved out and be inhabiting the moons around Saturn and Jupiter perhaps. But obviously things are pretty hot there. It's the Earth's return to its molten state. So that's the fate of the Earth in about 5 billion years' time, if it were to remain in its current orbit. So what happens then is the red giant slowly over time starts puffing out its outer layers, and that just takes about 10,000 years or so, just gently puffs out like that to expose its inner core. The inner core can have a temperature up to about 100,000 degrees. It's pretty hot, so it radiates ultraviolet light, and which ionizes all that outer material that's shed itself off the white dwarf, and it all starts glowing nicely, and you get one of these beautiful things called a planetary nebula. I'm sure you've all seen lovely pictures of these in books. Our sun is going to look like that at that point in time. Those planetary nebulas, slowly all that material will disperse about 30,000 years or something like that as a rule of thumb. That's a short time in the space of the lifetime of the sun, where I read in a book the other day that the planetary nebula, how long does it hang around for? If you put that into the lifespan of a normal human being, say 75, 80 years, that's 42 minutes. So it's a very short space, but they look very beautiful when you see them like that. But that's our sun's eventual fate. And then, of course, when that all disperses, you're just going to have a little wee tiny white dwarf, about sort of the size of the Earth or so, just quietly moving through space, cooling down. So that's chapter 1 and 2, putting the sun in context with relation to other stars in the galaxy. Let's open the hood and let's have a look and see what's going on, what is underneath it all and what's going on down there. So the sun, structure-wise, you split into the inner zones, which there's 3 of them, and there's 3 atmospheric zones. So we've got to look at the core, the radiative zone and the convective zone, and make up the 3 inner zones. And then we'll talk about the atmosphere, which is the photosphere, chromosphere, and the corona. And we'll briefly mention the solar wind and the heliosphere. So let's work our way through them. So the core is in here, as I mentioned. It's about 15 million degrees there. Why? It's because of all the mass overlying it and the pressure that's pushing down on it. It gets extremely hot and obviously high pressures for nuclear fusion to occur. As I mentioned, hydrogen goes to helium via the proton-proton chain, mainly, about 99%. A small percentage of it gets done by what they call the CNO cycle. That's another story. 600 million tonnes of hydrogen per second gets burnt out. I actually put that in yellow too, because a couple of the handouts I realised I left the million bit out, so I tossed that in. But yeah, 600 million tonnes per second of hydrogen gets burnt into helium. So the core goes out to about a quarter of the way out of the radius, so 0.25 radii. And what comes out of that nuclear fusion that's going on, really extremely the highest energy photons you can get, called gamma rays. They would sort of nuke us in an instant if we were exposed to them. And these little ghostly sort of elusive particles called solar neutrinos. And one of the reasons that we know what goes on in the core of the sun, and to what degree, even what sort of chains and so on, and what proportions, is through a process called detecting solar neutrinos. If anyone is interested in that, I actually have another little article I've done on the solving the solar neutrino problem. So just come up later, I'll leave them here and just grab them if you want. And it goes into a little bit more detail about the detection of solar neutrinos and how you can work back from there and work out exactly what's going on in the core of the sun through hunting for neutrinos many kilometres under the Earth. So I'll leave those there. Anyone's welcome to a copy of them. So that's the core. Then there's the radiative zone, which is here. That's when all these these high energy photons called gamma rays, they work their way, they call it a random walk, and they just keep knocking into particles, gets absorbed by a particle, gets readmitted, absorbed, readmitted, and it can take up to 170,000 years for a photon to work its way through this radiative zone, which goes out to almost 3/4, 0.7 radii it goes out to from the core. And it's very, very dense. Temperature ranges from about 7 million degrees here out to about 2 million degrees out of here. And it's just a series of just photons getting absorbed by particles, readmitted, absorbed, readmitted, and each time they lose energy, so the wavelength's getting longer and longer and the photons are getting less energetic and hot, to the point of when the photons, when they finally leave the surface of the sun, they are in the optic or the visual wavelengths, which we see. Radiative zone. That process occurs because it's just the right density and the right temperatures for that process to occur. Then you get out to the convective zone, and that goes right out to the photosphere. The average temperature is about 500,000 degrees Kelvin. It's less dense, and because it's less dense and less temperature, it goes through a process of the energy is transported by what they call convection cells, where the heat at the bottom of this layer comes up from the radiative zone and heats little packets, if you will, or cells of material. And of course, what happens when you heat something up? It expands. What happens when something expands? It becomes less dense. What happens when something becomes less dense? It rises, it floats. So you get little cells and packets that start to get very low density, and they slowly start to rise up in convection. It's like water boiling really off in your jug, and starts rising up to the surface. As it hits the surface, it expels that heat, which gets converted into optical or visual wavelength photons, and that's how the energy gets out. Now, when it gets rid of its heat at the surface of the sun photosphere, what does it do? It loses heat. What does something do when it loses heat? It contracts. What does something do when it contracts? It becomes more dense, which means it becomes more heavy, and it just quietly sinks back down again. And that's an ongoing conveyor belt in the convection. And that whole process is called convection. And it's just no different to boiling up your water in your jug. You heat it up from the bottom, from the hot element. The water, little packets of water become hot, less dense, start to rise. How long does it take? It takes the cells, the heated material, they travel at about 500 kilometres per second, and it takes about 10 days for the unit of material and heat to work its way up to the surface. So the end result, these high energy gamma rays, they end up as optical photons that end up leaving the surface. Fortunately for us, that's just right for us. The gamma rays, as I mentioned, would blitz us, so it just takes time. And as I mentioned, it takes up to 170,000 years for a photon to work its way up and get to the surface. And of course, it only takes 8 minutes and 19 seconds for that photon then, once it's left the surface, to get to the Earth, because it just travels unimpeded. So how do they know a lot of all this about the structure? Multiple reasons. One is, as I mentioned, hunting down and quantifying these solar neutrinos, told them what was going on and what exact amounts in the core. Computer models. You put in the laws of physics and what you do know, what you've observed, temperatures, you can work out the laws of physics and how plasma works, and you can actually get your models as well. But also what's called helioseismology. How do they tell the interior of the Earth? Seismology. You measure vibrations and reverberations and so on that are going on the surface and see how they move around on the surface, and that gives you a lot of information of the interior structure. And off the sun isolates in nice little patterns, very, very complex. But the bottom line is the surface isolations reflect the internal structure and dynamics of what's going on. So essentially it's acoustic pressure waves. In particular, that convection, there's a lot of turbulence going on down there in that convection zone with a lot of reverberations from that turbulence going right around the solar interiors. And that's another useful tool. It's a whole field of science, of astronomy, that they determine what's going on inside the sun. So the three atmospheres, the three atmospheric zones rather. So we'll start with the most closest one called the photosphere. That's opaque. So the surface, the sun doesn't really have a surface. It's like it's a hot gas plasma, but there's a certain region where you say you can't see anymore, so you call it the surface. The photosphere is that area. It's opaque, 400 kilometres thick through here. Temperature, as we've spoken about, 1,800 degrees. Its surface is very granular, which I'll show you in the next slide. And it's also the site of sunspots. You've probably heard of sunspots. I don't know if you've looked through a telescope, a solar telescope, and seen sunspots. So we'll talk about that in the next chapter. So let's have a closer look and see what the surface of the sun looks like. And that's what those granules look like. They're 1,500 to 2,000 kilometres across. They're often, because just the shape of Texas and the size, and being American, they often correlate the two. It's sort of roughly to the size of the state of Texas. So you're talking everything on the sun is in big scales, Texan scales, of course, big Texan scales, almost as large as a hat, Texan hat. So these granules aren't fine by any means. And what do these granules represent? The bottom line is they represent the heat coming up from these little convection little units, and I'll show you right here. So you can see the bright bits here, or you can see here, that is sort of, you can see a cell of heat coming up, another one coming up here, discarding all its heat, so that's a bright spot there. And as the cooler material starts to sink down, it's because it's cooler, so it appears to be dark. Still really, really hot by our standards, but it's cooler by the standards here, so it gets dark. And that's what's causing all these little granules. It's a very active place. Each granule hangs around for about 15 minutes before it's taken over by another small region of bringing up heat. But that's what the surface of the sun looks like from that rising plasma from the convection zone. Pretty cool. So moving on to the chromosphere, that's the next layer up in here. That's a crimson coloured, sort of a very fuzzy layer. Temperatures get up to about 25,000 degrees. So already you're starting a bit of an anomaly going here. Hang on a minute, I've always thought that things get cooler the further you get away from the source of something. Well, the temperature's gone up a little bit here from that 5,800 on the photosphere. It's the site of spicules, which we're going to have a close look at shortly. And here these are little spicules. They're essentially jets of plasma, jets firing up into the next layer called the corona. And here they are nice and close up. This is the chromosphere. Isn't that really cool? So these jets of plasma are very dynamic. They're not just sitting there like this or blowing up. They're shooting up constantly. They've got a diameter, once again, everything's on big scales, about 300 kilometres wide. So they're not tiny little wee things like hairs picking up. No, these are big sheets of plasma, hot charged particles. Each one of these. And there's usually, I've put here, between 3 and 10 million active spicules on the surface of the sun at any one time. The plasma shooting up at about 100 kilometres per second, and each spicule lasts for about 15 minutes, can get up to about 10,000 kilometres before the spicule falls away, and there'll be another spicule coming up and so on. So it's a pretty active place. What powers it? The fact that they hang around for 15 minutes, how long does a granule last rather? About 15 minutes. So the general consensus is it's probably this hot plasma coming up to form these granules that's probably driving these spicules as well. And that's the heart of a lot of research. And this is the movie I'll put on here. This is really cool. Let's get a close-up view.
A new NASA-funded study has revealed the origins of spicules, lengthy jets of plasma on the sun's surface. Scientists have been observing these long strands of solar material since the end of the 19th century, but their origins have been difficult to study because they're highly dynamic and short-lived. There are roughly 10 million spicules on the surface at any given time. They can grow up to 6,000 miles long and jet off the sun at 60 miles per second. Each one appears and collapses over the course of 5 to 10 minutes. Until recently, what drives these jets has been a mystery. In a new study, a model more than 10 years in the making was able to simulate spicules for the first time. Scientists compared the model simulations with observations from NASA's Interface Region Imaging Spectrograph, or IRIS, and the Swedish 1-meter solar telescope based in La Palma, Spain, and found they were closely matched. With an accurate model of spicules, scientists could explore their origins. The model reveals that a key component of spicule formation is the interaction between charged and neutral particles with the magnetic field. Scientists believe that this interaction drags tangled magnetic field lines up above the sun's surface, allowing them to straighten and expel solar material at high speeds, similar to a whiplash. The model also shows this whiplash process creating strong magnetic waves, which scientists think could participate in heating the sun's atmosphere and propelling the constant outflow of solar material called solar wind. Understanding spicules helps us to understand one of the ways that energy moves throughout our entire solar system.
It helps bring it alive, doesn't it? Just from simple little diagrams and drawings, it suddenly comes alive when you see these things. So, solar spicules, there's a word to take home, isn't it? Suddenly now you've got an image in your mind sort of what the surface of the sun looks like. It's fully alive. So let's move on to the corona. Here it is. It's the more sort of the outer and very ill-defined part of the solar atmosphere. And remember I sort of hinted towards the temperatures going up. So the temperatures in the corona get up to 2 million degrees. You might think, how does that happen? We're going to have a look at that. It's the site of all these solar activities sort of that I mentioned earlier on, solar prominences, solar flares, coronal mass ejections and so on. All that sort of activity happens in this outer layer called the corona. So let's talk further about that now. Okay, the corona is seen beautifully this is a total solar eclipse. See it all, there's all the material or hot plasma pouring out here. These are your activities going on inside your chromosphere. That looks nice in crimson colour. And the corona extends for millions of kilometres. It's very diffuse, it's very hot, tenuous gases, as I mentioned, up to 2 million degrees. There's also, they can look at the sun with what they call a coronagram, where you put a circular disc over a large part of your instrument to block out the glare of the sun, and then you can see all the activities that are going on in the corona. And this is a coronal mass ejection, which we will be talking about in our next chapter. So that's another way you can look at the corona. But you can't normally see it because the glare of the sun, of course, obliterates it. So the best time is these total solar eclipse or putting a coronagram on. So how do they know how hot it gets? The bottom line is they did spectral analysis of the sun, and they started seeing these funny spectral lines, and they thought, is this some new element? And then the penny dropped. Holy moly, this is highly ionized iron. In other words, iron with multiple electrons just totally stripped off it. And the laws of physics say you need up to 2 million degrees to get some of these highly ionized states of iron. So that's the evidence of how hot the corona is. But of course, it creates what they call the coronal heating problem. We think we've got heating problems. The sun's got a much bigger one. How on earth did it get so hot up there? Well, there's two sort of recent school of thoughts, nanoflares and Albion waves. So just looking at them briefly, We're going to look at solar flares. You'll see how they're huge, big events in the corona. But there's also little mini flares, about a billionth of the size of a normal solar flare, that are frequently all over they're very fast, low energy, and there's millions of them every second occurring on the surface of the sun. And they occur from a process of reconnection of magnetic lines, or magnetic reconnection. We'll talk about that more later on, but just in a nutshell, you'll see how there's magnetic loops that go over the surface of the sun that's responsible for a lot of the activity. And every now and then one of those loops gets unattached to the surface, flings itself around a little bit, and then reattaches to the surface of the sun. If it happens to reattach on a part on the surface of the sun where another magnetic field line is also going through, and this one here that's just reattached itself is of higher energy, the difference in the energy, which you're dealing in large amounts, gets quickly emitted and flung off into the corona. So if you've got a lot of these little nano flares, and you've got millions of them every second, only tiny, but there's millions of them every second on the surface of the sun, that is enough to heat the sun. So that's, things like the Parker Solar Probe that NASA's got on its way to the sun at the moment, the European Solar Observatory. All these missions in particular are going to be looking for this sort of activity, which they suspect is going on. The other one is these Albion waves, whereby with all the sort of twisting and distorting of magnetic field lines, which we're going to be talking about shortly, is magnetic field lines start shooting out perpendicular from the convection zone through the photosphere and high up into the corona, and they start isolating like waves. And of course magnetic lines take plasma up there, so suddenly you've got these big lines of hot plasma and isolating in wave form, and that also distributes a lot of energy high up into the corona. So these two mechanisms are the current two hypotheses of what's going on, what's heating that corona. Yeah, so let's also a lot of that coronal gas will escape. Obviously gets very hot up there. It's going to get, and I've mentioned it goes out. The corona goes out millions of kilometres. So some of those high-speed hot particles are going to escape from the sun, and we call that the solar wind. And it's the stream of charged particles, predominantly electrons and protons, with a few alpha particles, which are helium nuclei. Predominantly this, and they're firing out 4 to 6 billion tonnes per hour of material is flowing out, escaping from the sun's gravity and heading out yonder. And of course that comes past us as the solar wind. It interacts with the planets along the way, and that's, as you'll sort of see shortly with all the real strong activity, that's relevant to us. We've got a magnetosphere around our planet Earth, and that sort of deflects a lot of these highly energetic charged particles that can do us harm to our DNA, electronics and so on, but we've got a magnetosphere protecting us from the steady solar wind, which is different from some of the activity which we'll talk about. And I'll put this picture, because how many people, we've all seen this. It's an iconic picture of the Apollo 11 astronaut. That's Buzz Aldrin setting up. And what's he got there? That's what they call the solar wind experiment. So you look at most Apollo 11 shots, there's a picture somewhere of the solar, you'll see it up there, the solar wind experiment. That's what that is. And it was, of course, trying to capture particles from the solar wind. They folded it up afterwards and took it back to Earth for analysis. The solar wind extends for some time. It goes way out beyond the orbit of the planets, somewhere between 80 and 120 astronomical units, which is tens of billions of kilometres. Voyager 1 and 2 have already left where it meets the interstellar sort of wind, of charged particles from the rest of the galaxy all coming our way. Our sun's pumping them out, and it forms a little bubble right round the solar system, whereby the pressure of cosmic rays and particles, it sort of balances from the sun, balances the pressure of what they call the interstellar wind, and that's called the heliopause, is that little sort of the boundaries of that bubble, and the whole bubble's called the heliosphere. There was a big sort of fanfare about it when Voyager 1 and Voyager 2 both went through those regions, but that's what it's all about. It's the solar wind particles. So just briefly, in a nutshell, just recapping. So you've got your three inner zones, your core 15 million degrees, fusion of hydrogen to helium, producing these high-energy gamma rays. They work their way through the radiative zone, 170,000 years to do so, but in the process absorb, reemit, and so on. They lose their energy. They then heat up the base of the convective layer for these nice convection bubbles, if you will, or cells to slowly rise over a number of days to the surface, release their heat as wavelengths of light in the visual or optical range, which we see. And that, of course, occurs at the photosphere. We've got these little granules of rising cells, and then you've got these little spicules that go to make up the chromosphere, and then you've got this really hot corona going on here. So that's the sort of the structure of the sun in a nutshell, just summarising that section. So how about, let's talk about magnetic activity in solar cycles. What causes magnetic field lines? So you've obviously probably got you're thinking here, okay, there's magnetism going on because we've talked about it. What causes magnetic field lines and how do they cause solar activity? There's a few concepts to talk about. And the first one is the process called differential rotation, which you see at the surface of the sun. Those two outer layers of the sun that you see, the photosphere and also the convective layer just underneath it, because of their relative low density and temperature, they're still pretty dense, but they're relative to the rest of the sun, they behave like a fluid, like a liquid. So as they spin around the sun, the fluid motion is a lot quicker at the central, like equatorial latitudes, such that the photosphere and the convective zone are quietly rotating every 28 days around the equator, and it gets slower and slower the further you up. You get up to sort of polar latitudes, and the surface of the sun is rotating at about every 35 days to complete a full rotation. And that's called differential rotation, rotating at different rates according to your latitude. So that occurs at the sun. Okay, now, so I've mentioned that. You say, well, okay, I understand that. Where are your magnetic field lines coming in? I've mentioned the photosphere and the convective zone rotates in a differential way. The radiative zone is more solid. And because of that, it's more dense, and because of that, it behaves more like a solid, and it rotates all in uniform. Irrespective of what latitude you are within the radiative zone, you radiate exactly the same. About 27 days to complete a full rotation. So you're getting think, oh, okay, so what's going on between? And there's a surface, and there is a very small region they call the tachocline, and that's sits bang, or a buffer, if you will, between the more solid behaving radiative zone that's all going around at the same rate versus the convective area just above it that's going around different rates according to the latitude. And so as you could imagine, there's a lot of horizontal sliding and a lot of shear forces going on in that layer. And it is thought, certainly with the sun, that tachocline layer is where you're getting all this twisting and distorting and forces coming together. Most likely that's the region of the domino that's creating the magnetic fields of the sun. So the magnetic fields might start off all nice and orderly, like all good magnets. You have a north pole and a south pole. The sun has a polarity. And you've got these nice sort of vertical, if you will, magnetic fields. So you put that, then you add in the differential rotation of the sun, and look what happens. Suddenly all the magnetic fields around the equatorial latitudes are getting distorted a lot more, getting twisted around than these ones up here. And you can see slowly as the sun rotates and rotates and rotates over the days, those beautifully ordered magnetic field lines are getting distorted, building up with elastic energy, if you will, and are getting quite screwed up and more distorted and twisted. And it is the theory that it is the cycles of this twisting and distorting of these magnetic fields that cause a lot of the solar activity. And a good analogy, you might think, really, how does that all occur? A good one is, imagine a rubber band running up here. Imagine a rubber band, and what happens if you stretch a rubber band and tighten it, just crank it up. What happens? You've probably all done this. What happens? You get little kinks that springing up, little highly energetic little spots, and you get little parts, little knots, if you will, of the rubber band will flick up perpendicular. Go home, and if you haven't, go home and try it. Get a rubber band, stretch it, twist it, little knots. Yeah, perpendicular knots. So suddenly, if you're doing these, imagine these were rubber bands, the magnetic field lines. You start twisting and distort them. You're going to get perpendicular little magnetic field lines popping up through the surface, doing a little bit of a loop and diving back again, just like your rubber band. And that's what's causing these solar activities, which we'll look into now: sunspots, solar prominences, solar flares, and coronal mass ejections. Now, the other thing I'll mention, I just mentioned it briefly in that slide, is the sun gets cycles of these. It goes through what's called 11-year cycles of activity from what they call solar minimum and solar maximum. And as the names indicate, solar minimum is when the sun's relatively quiet, so those magnetic field lines are probably more realigned and there's not too much going on in the sun. But as the sun rotates around and around, over the next sort of 5.5 years, the twisting gets more and more and more, and you start getting more of those little perpendicular little loops upwards, and you start getting more activity on the surface. In terms of where are we here with the cycle, the last cycle minimum was we entered into a new cycle at minimum about December 2019. So the next solar maximum will be, to have a good look at the sun, will be July 2025. But I've got some slides just to illustrate the solar cycle a bit more. So here's just an example. 1996 was solar minimum, and here it is going through an 11-year cycle to 2006. See, it's quite a little bit of activity going on, a little bit more activity, more activity, more activity. 2001, woohoo, you know, the sun was just writhing with activity, then it all starts to settle down again. And probably what's happening is these magnetic field lines are all nice and orderly here. As the sun's rotating around, they're getting more twisted and distorted and so on. They're having a right party going on over here, and slowly it's starting to correct itself. So that's the 11-year solar cycle. And sunspots are one of the visible things that you can actually monitor on the sun, and they're a good indicator of the level of activity that's going on the surface of the sun. If you see a lot of solar spots visible at any one time, you know there's a lot of activity. If you don't see them, there's not a lot of activity going on. And we're going to I'll show you in my next slide what exactly sunspots are, but you've probably heard of sunspots, and that's what they are. These dark patches that typically occur in pairs and groups on the surface of the sun. And what they are, the dark patches, they're actually still bright and hot, but in comparison to the surrounding surface at 5,800 degrees, they're cooler, so they appear a lot darker. And what you've got is concentrated, or regions of concentrated magnetic fields that are suppressing the heat coming up from the convective layer. So that's what's causing them to appear to be a lot cooler. And let's look at it side on. I've got another one to go, but here we go. Here's some sunspots. To give you an idea of the size of them, remember what we said, the scale on the sun, everything's huge. That's roughly the size of the Earth compared with these sunspots. I don't know if you've looked through a solar telescope. If you haven't, it's well worth it. It's pretty cool. And you can see the sunspots. Each of those sunspots most likely is much larger than the Earth. The typical range is about 1,500 to about 50,000 kilometres across. They can get up to 80,000 kilometres across. They typically last for anywhere between 1 and 100 days, and often you get groups of them that appear for about 50 days. I think this is a good slide describing exactly what they are. So you've got magnetic fields. Obviously the field lines are running through here. You get these highly twisted and distorted little patches of magnetic field lines. They pop up through the photosphere, loop over like that from a north, and they find a little south pole for themselves, loop back on and rejoin into the surface of the photosphere, and so on. And you can see if heat's trying to come up here, the plasma tends to get trapped under all this loop of magnetic field lines, and that's what causes sunspots. The other thing is that solar activity, we've mentioned, goes through that 11-year cycle. Here's just some dates and so on where we're going. As I mentioned, we're heading towards the next one in 2025. And you'll notice that the sunspots, this is a sunspot count, and these are your years. So just through counting sunspots shows you beautifully the solar activity cycle of the sun every 11 years. And the other interesting thing, this is a famous butterfly diagram, is that as the solar cycle progresses towards solar maximum with more activity, the sunspots appear or tend to form closer to the solar equator. So when the sun's quiet, you've got few sunspots. They tend more to be out in the equatorial parts of the latitudes. Sorry, of the mid latitudes of the sun. And as the activity cranks up, you start to see more and more sunspots closer and closer to those equatorial latitudes. And I've just done this here. I've just put 3 lines. These were the times of solar maximum, and you'll see here at those particular times, you're getting more sunspots are starting to appear at the equatorial regions, here, here, and here. And it's quite a cool graph, which I put in the handout, where you can actually, for yourself, correlate it. So here's the 2 graphs correlated together, and it shows you where the solar minimum is, where the solar peaks in activity is at solar maximum, and you just carry the lines up, and there it goes in beautifully with, as you're heading towards solar maximum, you're getting less and less sunspots in those mid-latitudes and more in the equatorial latitudes. So let's talk about the real grunty, the meaty stuff now. So solar prominences. So essentially what you've got here is instead of like just a small little magnetic loop causing one of these sunspots, you've suddenly got a much bigger magnetic loop going on here. And of course the hot plasma, it's charged particles, it follows the magnetic fields, and you get these beautiful big arches and loops. Once again, they've put in, there's the size of the Earth compared with all this plasma that's forming this beautiful big large dense arch cloud of solar material. So that's solar prominences. They typically form over about a day or so, 24 hours, and they typically can last anywhere from a few hours to a few months, so they can hang there for some time. And I've put here, the magnetic field is anchored to the photosphere, so you get this lovely big loop that's anchored there. And that's a solar prominence. Now, if that's looking at it side on, so what say you're looking directly on, just the orientation of the prominency at the sun, it looks a lot darker because it's cooler, the plasma's come up off the surface, so it's relatively cool. It's still damn hot, but it's relatively cooler, so it looks like this sort of dark streak, and that's called a filament. So if you see a sign that says, oh look, there's a filament, you think, oh okay, we're looking directly down on a solar prominence. So solar flares, what are they? We've already talked about these mini flares that are probably heating the corona. So a solar flare is the same thing. You get these magnetic loop that goes up. One end of the loop just goes berserk and goes rogue. It's almost like whiplash. It's flying all over the place. Eventually it re-anchors itself down. And if it happens to re-anchor itself down where another magnetic loop is also going into the sun, and if there's a difference between the energy, and more likely there will be, the difference in energy is then quickly expelled and given out into the corona. And we're talking huge amounts of energy, whereby the gas and that's the plasma that's around that region as that magnetic reconnection goes on gets accelerated very quickly to the speed of light. And what do charged particles do when they get accelerated? They start emit photons light. So these things are really highly energetic and they're quick bursts. And so they're releasing highly charged particles, and those charged particles release high energy X-ray and UV photons. In fact, it's the X-ray photons, the observation of those, and their energy levels is how they actually grade solar flares. So that's through a process called magnetic reconnection. So the brief, almost like a sneeze, an analogy, a solar prominence, I thought of this analogy the other day. A solar prominence is like a bit of reflux. It comes up, but it goes back down to the surface again. This is like a sneeze, a quick sudden poof burst. Not much material, it's mainly all action and burst of energy. And a solar or coronal mass ejection, which we're going to have a look at next, is a projectile vomit. Here we go. See, look, here's your projectile vomit. So you've got no little loop, no little belch or burp or reflux going on here, my friends. It's full on. So this is called a coronal mass ejection, and obviously it's huge masses of hot plasma being quickly and huge energies released into the corona. They occur at solar minimum about every 5 days or so, but at solar maximum there's several going on every day. That's when the sun's really, really active. And during one of these events, billions of tonnes of material is just lifted off the surface of the sun and accelerated to it. You're talking of velocities about 1.6 million kilometres per hour, very, very quickly. So these are huge events, and it's these events in particular that are really important to us on Earth, Why? Of course, then you suddenly get these big bursts of charged particles heading our way. We're very vulnerable as a technologically advanced society. Astronauts in the ISS, satellites, power grids, communication networks on the Earth and so on. And if you don't think that's a problem, go and ask the people in Quebec. I think in March 1989, Quebec was without its power for for about 24, 48 hours because of one of these coronal mass ejections. And they call it space weather. So that's a lot of the research now, is trying to predict space weather. What's causing these coronal mass ejections? Can we predict them? If we know one's about to go, of course you can shut satellites down, tell your astronauts to hide, in a lead protected area. You might power down your power networks and so on. So here's a really cool little video of the solar flare turning into a coronal mass ejection, which then starts raining back, called coronal rain. So 4 minutes of the video, it works out to which is 24 hours. So it's a 24-hour recording put into 4 minutes, and this really brings the sun alive for you. Amazing. That certainly highlights, doesn't it, how dynamic and active the sun is. So you imagine that at solar maximum, those things going off throughout the day. Pretty messy day on the sun, I'd say. But, so now here's another, I just want to make sure I haven't missed a slide. No, I haven't. It's cool. And this is in the handout. So this is a really cool address on the internet to have a look at. It's a 30-minute video from NASA, the sun in 4K, ultra high definition. DHS should be HD, but anyway. That's cool. That's really, really cool. So you can get that off your handout. So just the sun in a nutshell, just summing up again. So you've got your core here, which is out to about a quarter of the radius of the sun, 15 million degrees because of the pressure coming down on it from gravity. Hydrogen, 600 million tonnes per second of hydrogen getting converted into helium, which gives off high-energy gamma rays and solar neutrinos. The solar neutrinos, by the way, just zip out within minutes. They're very ghostly-like. You're welcome to read more about those. The high-energy gamma rays, they go through the radiative zone, take up to about 170,000 years to do what they call the random walk. They then heat up the lower part of the convection zone with these sort of cells, if you will, take a few days to rise up to the surface, give their energy out as in optical or visual wavelengths, which we then see. They sink back down again. The surface of the sun, the photosphere and the convective zone has got a differential rotation. In other words, it rotates at different rates according to its latitude, as opposed to the radiative layer, which doesn't do that. It's all uniform. So you've got this tachocline here, which generates these, thought to the region where it generates on large scales the magnetic field lines. That differential rotation twists and distorts the magnetic field lines, causing them to pop up above the photosphere, causing all these sort of activities here, such as you've got solar prominences, these sunspots, and of course the coronal mass ejections, and you've got your solar wind going on as well, and of course you've got these little spicules going on constantly as well. So that's the sun, the structure and what's going on in the sun in a nutshell. So once back to our 3 sticky messages, remember over 99, in fact it was 99.86% of the mass of the solar system is the sun, and it's just vital to life on Earth. We wouldn't be here without it. It generates energy, so that very clean and a very efficient form of nuclear fusion, hydrogen into helium. And solar events are due to this distortion of those magnetic field lines from that differential rotation at the surface. So I hope you've enjoyed the sun, our nearest star. What's going on and why? Thank you.